Hey everybody, Zach here. So I want to go ahead and relate electric forces and fields between physics 1 and physics 2. So in physics 1, you would have learned force equals Gmm over r squared. And this was some attractive binding force that pulled two masses together. This is why the moon goes around the earth goes around the sun. There's some attractive binding force overall that pulls them all together. But now in physics 2, the electric force is going to be KQQ over r squared. Notice the similarities here between these. The main differences is we know that masses are going to be greater than zero. Masses are positive. Over here, though, forces, with charges can be positive or negative. That's why here we have absolute values, and well, here on the left, we didn't. So with these charges, well, it depends. Are we going to have attractive or repulsive? And we know with charges, opposites will attract, and like charges will repel as a result, okay? So that's the similarities. Now, moving on. Let's say we talk about, again, physics 1 for a second. We have a mass, and we have the Earth, and here's the ground right here. Okay, here is the Earth. So which way is this mass falling? Well, it's going to fall to the ground because we learned that there's some force due to gravity. But here's where it comes in. This is because there's some gravitational field that's pointing downward toward the Earth, okay? So the force of gravity is equal to mg, where force is a vector and gravity is a vector. And so there is a gravitational force due to the gravitational field, okay? Which we know that since mass is positive, they're going to point in the same direction. If gravity is pointing down, then the force of gravity is pointing down as well. And so therefore, when we're looking at this gravitational field is newtons per kilogram. That's the units, okay? Now, of course, you know it as meters per second squared, but also if you solve it like so, it's actually newtons per kilogram. So gravitational field is force over mass. If we take a charge Q and we experience some type of electric field now, well, it depends which way this is going to go, because we know that the electric force is equal to the charge times the electric field. Force and electric field are, again, vectors. The units for electric field are going to be newtons per coulomb of charge. So notice the similarities here between physics 1 and physics 2. The difference is mass is always positive. Over here, if the charge is positive, then they go in the same direction, the force and electric field. However, if the charge is negative, then they go in opposite directions. So if this charge is positive, then the force and electric field go in the same direction. If the charge is negative, well, then the force and electric field are going to go in opposite directions. So that's the connection. Now, putting this all together, what do we have so far? We have 2 and eventually 3 equations. We have force equals K, Q, Q over R squared. And we have force equals Q, E. Vector, vector, vector. Okay. Well, putting these together, well, it looks like the only difference is from electric field to force, we have an extra charge Q. So therefore, if we go ahead and divide a Q out, that means electric field would be KQ over R squared. So if I substitute this in right here, I will get that equation overall. So that's the connection between these 3 equations that starts off forces and electric fields.